So we are starting with one of my favorite topics. So if I'm overly excited, this is why. And it's because we can apply intermolecular forces. We learn it at the very beginning of chemistry, but we can apply it all the way through organic chemistry. Lots of connections. And before we get started with it, I just want to remind you of what a solid, a liquid, and a gas look like at the molecular level, because it would also help us explain some of the types of intermolecular forces and why we see certain trends. So it helps us explain some things that we see on an everyday basis. Well, maybe minus this one, but it will help us explain why no matter how hard this guy tries, he is never going to jump through that wall. More simple things like why sugar dissolves in coffee and why a gecko can walk across different surfaces. It's all related to intermolecular forces. And I want to start because it's related by just reminding you of polar versus nonpolar molecules. Okay, and that is related to the 3D shape. It all builds on itself. So if we have something with a linear shape, assuming that both of the substituents at the end are the same or both groups, we're going to have something that is nonpolar. Same is true if we have something that has a trigonal planar shape. Assuming all three of these groups are the same, we'll have a nonpolar molecule. If we have something that is tetrahedral, it depends on what we have as those substituents. So it can be nonpolar or polar, depending on whether we have symmetry or not. If we have something that is trigonopyramidal, it will always be polar because we break that symmetry with the lone pair of electrons. And if we have something that is bent, like water, it will also always be polar because of those lone pairs. So we need that information to think about intermolecular forces. So just to give you an overview, all of this that we're going to learn is going to be the interaction of positive and negative, or partially positives and partially negatives. So just a reminder about bonding in general, if we have something that is nonpolar covalent, so if we have two atoms that are being held together in a chemical bond, if we have equal sharing, we could also have unequal sharing if one of those atoms wants the electrons more or is more electronegative. It'll pull electron density towards itself. And when it does that, it creates a partially positive on the side where we're pulling electrons away and partially negative on the side where we are gaining the electron density. So this will be polar covalent, and then just flat out ionic if we're not sharing electrons at all. Okay, so I want to show you if I have, for example, a polar molecule, again, since one of the sides wants the electrons more, we get a partially negative and partially positive. And now if we look at two separate molecules, the partially positive of one molecule can interact with the partially negative on another molecule. And this just keeps on going. So no matter what type of specific intermolecular force we're talking about, something like this will be true. Okay, so now that we have an overall idea of what's going on with intermolecular forces, let's talk about the specific types. And we're going to start with the one that is the weakest. And this is called a dispersion force, or you've also probably heard London dispersion force. And notice that we just have two neon atoms, and you may want to pause the video. Just look at what's going on with the electrons. Two separate atoms, what's going on with those electrons? And for this, the only thing that we need is for it to have electrons, because electrons are not static. They're always moving around. So if you look at this picture here, we see that at any given moment, maybe the electrons are sitting more so on one side than the other. So that generates a partially negative on one side and partially positive on the other side. And then those two different atoms can interact. Okay, so it's the weakest type of intermolecular force or attraction. The only requirement for this one is it has to have electrons. So every single atom molecule, all of those have London dispersion forces. Everything has London dispersion forces. If it has electrons, that's the case. Okay, so all molecules have this. Now, the big difference that we're going to see from some of the other types of intermolecular forces is that it is the result of an instantaneous or temporary dipole. So it's not a permanent partially positive and negative. It's one that is just made at any given moment. Okay, so For nonpolar molecules, this is the only type of intermolecular force it will have. So the very first thing I would do with these types of problems, if you're trying to figure out the intermolecular forces, you need to figure out whether or not the molecule is polar or nonpolar. So that's why we did a little bit of review of that. Okay, and if we put this all together, let's say I had lots of different nonpolar molecules, but again, we have these instantaneous or temporary dipoles. All of those partially negatives will interact with the partially positive on the molecule next door. And then we just can have a lot of these interacting or holding them together. I want to remind you that when we're talking about intermolecular forces, we're not making or breaking bonds. That's different. That's a chemical reaction. This is just an attraction between different molecules, so inter. Okay, I want to give you an example of how we would apply this. Right? So we have a bunch of different what we call alkanes. We're going to get into this more a little bit later, but they have carbon and hydrogen. They're hydrocarbons. We also call them alkanes if they have only single bonds. And we can look at, as we start to grow the number of carbons in the chain, we have a difference in the boiling point that we see for that particular molecule. I would pause the video and think about this for a moment. How would you explain this? So let's start with the trend. As we get more carbons in the chain, our boiling point is getting higher and higher, right? If we think about what's happening with the boiling point, or what's actually happening at the molecular level, we're going from the liquid phase to the gaseous phase. And to do that, we have to pull the molecules far apart. So I want you to just imagine the molecules getting further and further apart as they go into the gaseous phase, right? So now we want to think about, well, why does this one have such a higher boiling point? And what does that mean? So a higher boiling point means it's going to take more energy in the form of heat to get that molecule to go from the liquid phase to the gaseous phase. Or it takes more energy in the form of heat to pull those molecules apart. So the analogy I like to use is imagine, and I always imagine my daughter doing this because this is something she'd probably do. Hold your arms out and imagine just putting super glue going all the way down your arm, okay? And then go ahead and put your arms together and stick them together. So that's going to be represented by, or analogous to, this larger or longer chain, all right? So think about that. And then alternatively, ball your fist up and put a little bit of super glue just on your fist and try putting your fist together. Which one is going to be harder to pull apart? Okay, so it's going to be the one where you have super glue going all the way down your arm. You have more surface area or more points of contact. So as I have more surface area, I have more intermolecular forces, or stronger intermolecular forces, more of those partially positives and partially negatives holding the molecules together. So it's going to take more energy in the form of heat to pull those molecules apart. And what you see is a higher boiling point. Okay. Let's look at another example. So now we have what's called constitutional isomers. We have 3 different molecules that have the same chemical formula, but their connectivity of atoms is different. For the boiling point, we see a similar trend. The one that has a long linear chain is going to have a higher boiling point, because again, we have more surface area or more points of contact, stronger intermolecular forces. But if we look at the melting point, and I want you to look at the 2 extremes, we have a long chain, and then we have kind of a rounder molecule. And I would pause the video and think about this. The trend is actually different for a melting point. The one that is rounder, or the one that seems to have less surface area, because it's not a long linear chain, actually has a much higher melting point. We see the opposite trend for melting points. So this is something I would star in your notes. So to make sense of this, we need to think back to what it means to melt, right? If we're melting, we're going from a solid to a liquid, okay? And we want to think of what a crystal lattice looks like. So if you think back, if we try to explain this, to what a crystal lattice looks like, and I always remember kind of the cube that has the balls that represent the molecules, and they're packed tightly together. Okay, so if we think about this, if we're in the solid phase, and let's write solid here, we want those molecules to be rounder because they can actually pack in tighter. Okay, so if I have a molecule like this that is kind of more, has more of a spherical shape versus a molecule like this that is more linear, this will actually pack into a crystal lattice much better and make the molecules harder to pull apart. So if we're pulling the molecules apart and they're packed in tighter, it's going to take more energy in the form of heat to pull them apart, and that is why we get a higher melting point. Okay, let's look at another trend. And for this one, we have 3 different molecules, and they're all halogens. Remember, halogens like to exist in pairs. One thing that we see is at room temperature, chlorine exists in the gaseous phase, bromine is a fuming liquid, and iodine is a solid. So why are these 3 so different at room temperature, right? I would pause the video and think about that. I want to give you a hint first. We know that all 3 of these molecules are nonpolar molecules, so they only have London dispersion forces. Go ahead and think about it for a moment. Okay. If we look at our best friend, the periodic table, or your other best friend, we know that iodine has a lot more electrons. So when we have a lot more electrons, the extent of that partially positive and negative, those temporary dipoles we were talking about, it happens to a much greater extent for iodine because it has a lot more electrons. We call this polarizability, or the ease of electron cloud distortion. Happens a lot more readily or to a greater extent for iodine, and that's why it's a solid at room temperature. Takes a lot more energy in the form of heat to get it to go into another phase. Okay, here's one application of this, and I'll also post a video so you can look into this more, but a gecko can walk across these little tiny surfaces and even go upside down, and it actually sticks to the surface. It turns out if you zoom into their hands and feet, they have these tiny little nano hairs. So they have just dispersion intermolecular forces with whatever surface, so partially positives and negatives from their tiny hairs interacting with the partially positives and negatives on the surface. But if you zoom in and you have millions of those, even though it's a very weak intermolecular force, if you have a lot of them, it's strong enough to hold them to the surface. So there's a lot of research on how we can actually mimic what a gecko does. My husband is a mechanical engineer, so I say he likes to play. I always think about his office in grad school where they had all these flying robots, windy stairs that leaned up to a workspace, a couch, which is unheard of. We don't see couches in chemistry labs, but they do research to try to mimic something like this. So I want you to stop and think about what percentage of your body would have to be hands and feet in order to do what a gecko does. Go ahead and think about it for a moment. It's actually around 80%. So we would need a lot more surface area to be able to do that because of our weight. Now that we have the basics, let's move on to another type of intermolecular force. And the next strongest is going to be a dipole-dipole interaction. And here are the requirements. Okay, so the first thing is it's stronger than a dispersion intermolecular force. It results from a permanent dipole. So I'm going to circle that. So the molecule must be polar for it to have this type of intermolecular force. Again, we were saying when we're trying to figure out what type of intermolecular force, you always start with determining whether the molecule is polar or nonpolar. So here's one example, HCl, and we know that chlorine is more electronegative, so it pulls electron density towards itself. So the hydrogen has a partially positive, the chlorine has a partially negative. And if I have a neighboring molecule, the partially negative on the chlorine can interact with the partially positive on the hydrogen. Okay, here's one example, and that's going to be nail polish remover. The active ingredient is going to be acetone. So this is the structure of acetone minus some lone pairs here. And it's a polar molecule because we know that this carbon-oxygen double bond, we know that there's always going to be a dipole there. There's always going to be a partially negative on oxygen and a partially positive on carbon. If we look at the structure of one of the dyes, here's an example of a dye in nail polish. Look at the molecule here. It's also polar. We have positives, we have negatives, we have lots of oxygens. This is also going to be a polar molecule. So it goes back to likes dissolve like. The acetone is polar. The structure for the ingredient in the nail polish that gives it its color is also very polar. They can interact. Here's another example. This is sucrose. This is table sugar. And if you look at the structure, what you notice is that it has lots and lots of OH bonds. And we'll learn more about sugars at the very end of organic chemistry. But something we want to keep in mind is that coffee is mostly water. We know that water is a polar molecule. We know that it has a bent shape. So again, we have two very polar molecules. They can interact, and that's why the water in the coffee can dissolve the sucrose or table sugar. Okay, so now we want to take a look at whether or not certain molecules have dipole-dipole interactions. So what I recommend doing is pausing the video and working through these, but the very first step will be drawing the 3D molecule. So draw the Lewis structure and then add VSEPR theory. Okay, so once you do that, here are the structures you get. So this is dichloromethane. It's a common organic solvent. This molecule is going to be polar. So we would expect it to have dipole-dipole interactions. For carbon tetrabromide, notice that we have symmetry now. All four of these dipoles, if we draw our dipole moments, they're going to cancel each other out. So anytime you have all the same substituent, this is going to be nonpolar. Okay. So we would not expect this to have dipole-dipole interactions, but for dichloromethane, we would. For carbon dioxide, this is going to be nonpolar. Remember that the dipoles cancel each other out here. They go in the opposite direction. So we don't expect dipole-dipole interactions here. And then if we look at formaldehyde, we have a dipole here. This is going to be a polar molecule. We would expect to see dipole-dipole interactions. Let's move on to another example. So for this one, we're trying to rationalize the difference in boiling points. So the first thing I would look at are the functional groups in the molecule. And for this one, I'm just going to split this in half. For these two molecules, we have alcohols. So we expect them to have a higher boiling point because they have stronger intermolecular forces. We know that these have just dispersion. And both of these, they also have dispersion, but they also have dipole-dipole interactions. So automatically that splits our problem in half. And then it becomes, well, the shape of the molecule. This one is a long linear chain, and this molecule we have some branching. So remember we talked about surface area? This one has a lot more surface area or more points of contact, which means stronger intermolecular forces, which means it takes more energy in the form of heat to pull those molecules apart, or a higher boiling point. On this side, if we want to differentiate between these two, it's the same reasoning. We have a long linear chain that has more surface area versus a molecule that has a rounder shape. So I would always start with listing the types of intermolecular forces, and then you can figure out the shape of the molecule and how that comes into play. And then just make sure you're paying attention to whether you're talking about the boiling point or the melting point because they are different. Okay, so now let's move on to another type of intermolecular force, and this is hydrogen bonding. But I want to remind you that it's not an actual bond, it's an interaction. So I always say hydrogen interaction, but hydrogen bond. It is a specific type of dipole-dipole interaction. So it's still a type of dipole-dipole, but it is stronger. For this one, you must have these specific bonds in the molecule, an OH, an NH, or HF. Otherwise, you don't have this type of interaction. It also results from a permanent dipole. If we look over at this interaction, let's see specifically what is interacting with what. I would go ahead and pause the video and take a look at it. We have a lone pair from the oxygen interacting with this partially positive hydrogen. So that is the type of interaction we're looking for. And this is why water has such a high boiling point. It can form these hydrogen bonds in these strong networks of one molecule of water, hydrogen bonding to many other water molecules. And one application of this is surface tension. It's the reason why the spider can walk across the water. It's the reason why when we see the drips coming out of a sink, it has a round shape. It's because of surface tension. It's because of hydrogen bonding. And here's a picture of what's going on. So if we imagine that each of these circles represents a water molecule, this water molecule can interact with all of these water molecules nearby via hydrogen bonding. But the ones that are on the surface, because they're not surrounded by as many water molecules, because some is exposed to air, it doesn't have as many hydrogen bonds, so it compensates by pulling in these water molecules closer. That's called surface tension, and it creates a network for something like a water spider to walk across. Same idea for the water droplet. The water molecules on the inside can hydrogen bond with all these around, whereas the ones that are on the outside exposed to the surface, the air, they can't hydrogen bond to as many water molecules, so in turn they pull in closer, and it creates that round shape. So we want to minimize the surface area. Another example of this is our DNA, which I find so fascinating because it's a simple intermolecular force, not even a bond, just an interaction, but it's strong enough to hold our genetic makeup together. So here's another question, another example of how we apply this information, and that's where we're going. We want to be able to apply the concept. Why does acetone evaporate from the skin faster than water? I would go ahead and pause the video and think about this. I would always start in the same way by listing the types of intermolecular forces. So for this molecule, we have dispersion, and same here, we have dispersion for water. Only requirement is electrons. For both of them, we do have a polar bond in the molecule. It's a polar molecule, so we have dipole-dipole, and we have dipole-dipole. But since we have an OH bond in water, we also have hydrogen bonding. So it has stronger intermolecular forces. If we think about when we're evaporating, we're going from the liquid phase to the gaseous phase. So this is an example of a boiling point. Because we have stronger intermolecular forces, we would expect water to have a higher boiling point. And we would expect the acetone to have a lower boiling point, and that's why it evaporates from your skin a lot faster. Let's look at another example. If we're comparing boiling points and we have water and we have ammonia, I would also go ahead and pause the video and think about this. So water has an OH bond, so it has all three types of intermolecular forces: dispersion, dipole-dipole, and hydrogen bonding. And so does ammonia, though, because we have an NH bond. So the big difference here is for the water, I have two lone pairs, so I can form more hydrogen bonds to other water molecules, whereas the ammonia only has one lone pair. This is the last type of intermolecular force we're going to talk about, and it's the strongest. This is called an ion dipole intermolecular force. It's very strong. We must have two components. We need to have a polar molecule, but we also need to have a full-out ion, so like sodium or potassium, a full-out ion. If I have an anion, that negative charge is going to interact with the partially positive on a polar molecule. If I have a cation, it's going to interact with the partially negative on a polar molecule. And one example of this is table salt, so sodium chloride, why it dissolves in water. And it's because the hydrogens can interact We know those are partially positive. It can interact with the full out negative charge of the chloride, and then the sodium can interact with the partially negative charge on the oxygen of the water molecules, and that pulls the two ions apart, so that solute-solvent interaction is much stronger. So here's one example of what's called an ammonium salt. A lot of the active ingredients in different medicines, you'll see this HCl. So they make it into an ammonium salt, and we want to think about why. Okay, so go ahead and pause and think about that. Once we do that, we generate a full out positive charge and full out negative charge. So we can have some ion dipole interactions. And if we think about what our bodies are mostly made up of, it's going to be water. So these tend to be more soluble. A lot of times this starting compound will be a viscous liquid, and this will be a solid. So the shelf life is a lot better as well. So there are a few different reasons why a lot of times you see that HCl salt. One other example of this is ion transport in cells, and I just couldn't help myself. But we have potassium and sodium that have to get across the cell membrane, and we can use water molecules to do this because we can have that strong ion dipole interaction. So to summarize, we've talked about 4 types of intermolecular forces. Dispersion, which is going to be the weakest, which is the result of a temporary partially positive and negative. Dipole-dipole interactions, but now you have to have a polar molecule. A hydrogen bond, which is a type of dipole-dipole interaction, if you have a OH, NH, or HF bond. And then for an ion dipole interaction, the requirement is you have to have 2 components, a full-out ion, and you also have to have a polar molecule to interact with it.